Vector operations can be greatly simplified if they are expressed as Cartesian vectors in the Cartesian coordinate system. The three-dimensional rectangular coordinate system, also known as the Cartesian coordinate system, is made of three number lines that are concurrent, meaning that they intercept each other at the origin, and also perpendicular to each other. These three number lines, known as the x, y, z axis, divide the space into 8 octants, as demonstrated by the 8 cubes with different colors in this image. The reason why this is called a right-handed coordinate system is because the positive directions of the three axes follow the right-hand rule, which means that if you roll the four fingers in your right hand from the positive x direction towards the positive y direction, as shown in this image, then your thumb will point towards the positive z direction. So if we transfer an arbitrary vector A into an established Cartesian coordinate system, with the tail of the vector fall on the origin, then we can first apply the parallelogram law to resolve vector A into two component vectors, AZ that falls along the z-axis and A prime that falls within the xy plane. Then we can apply the parallelogram law again to resolve vector A prime into the two components AX along the x-axis and AY along the y-axis. We can prove that A equals to AX plus AY plus AZ, and therefore AX, AY, and AZ are the three rectangular components of vector A. Since a vector needs to be described by two parts, its magnitude and its direction, we can separate these two parts by defining unit vectors. For any arbitrary vector A, its unit vector UA has the same direction but a magnitude of unit length 1. Therefore, vector A can be expressed by its magnitude A, which is a scalar, multiplied by its unit vector UA. As mentioned earlier, a unit vector can be defined for any arbitrary vector A. However, there are three special unit vectors, I, J, and K, which, as you can tell, have their own names. They are special because they are designated to the directions of x, y, and z axes respectively in the Cartesian coordinate system. Therefore, using the unit vectors I, J, and K, the component vectors along the x, y, and z axes can now be written as AXI, AYJ, and AZK, with AX, AY, and AZ being the magnitudes of the component vectors. When a vector is expressed this way, we call it a Cartesian vector. And by applying the Pythagorean theorem twice, we can derive that the magnitude of the vector A equals to the square root of AX squared plus AY squared plus AZ squared. To describe the direction of the vector, we can use the coordinate direction angles alpha, beta, and gamma. Alpha is defined as the angle between the vector and x-axis, and similarly, beta and gamma are angles between the vector and the y and z-axis respectively. If we highlight the plane made by the vector A and the x-axis, shown as the blue shaded area, then according to trigonometry, we know that cosine alpha equals to AX divided by A. Similarly, as shown in the right triangle made by the vector and the y-axis, cosine beta also equals to AY divided by A. And again, cosine gamma also equals to AZ divided by A. And then, because the unit vector of vector A, UA, equals to vector A divided by its magnitude, UA can be derived as AX over A times I plus AY over A times J plus AZ over A times Z. Or UA equals to cosine alpha I plus cosine beta J and plus cosine gamma K. And since the magnitude of unit vector is always 1, therefore we can come to the conclusion that the sum of the cosine squared of the three coordinate direction angles for any Cartesian vector must equal to 1. Therefore, when you perform Cartesian vector addition or subtraction, all you need to do is to sum the I, j, and k components of the vectors up separately, and those will become the new I, j, and k components of the resultant vector.